Welcome back to our lesson on large language model. So today we're going to talk about self-attention, and here we are going to discuss about how and what to process, how to process and what to process. So let's begin by setting a fixed random seed, and here's why it matters. So first of all, let's have this code. So in this case, reproducibility or reproducibility is critical when building deep learning models, large language model, or even machine learning model. So without it, the same script could yield different results every time you run it. So this happens because deep learning involves randomness from weight to the initialization, shuffling datasets to drop out layers. So by setting seeds, we freeze that randomness so you can trace your steps and reproduce experiments exactly. So I am actually talking about this one. So we set seeds across the three common sources of randomness. First, we have the Python random, NumPy's pseudo-random generator, and PyTorch's random function. So this becomes even more important during the model evaluation or hyperparameter tuning, where small variations can lead to misleading conclusions. Let's execute this one. And the next thing that we're going to do is to load our data, our text file. So let's have this code, and this code loads the text file. So we now load the raw text data that fuels our large language model or our language model. We store our dataset. In this case, we use the Wizard of Oz as a .txt file under a folder named data, or is path. That join dynamically constructs the path file to make it platform independent, so it works on Windows, even Mac OS, or even Linux. The file is open in read mode, and we explicitly define the encoding as UTF-8 for us to avoid any issues with respect to special characters or non-English characters. The full text is loaded as one long string. So this is necessary for the tokenizer, which operates on a continuous stream of characters. So if you're using your own dataset like emails, books, or transcripts, just replace the file name and make sure it's pre-clean if needed. So for example, there is no HTML tags or malformed characters. So let's execute this one. So let's now go to tokenizing and preparing for sequences. So let's name this one tokenizing. Now let's bring in the tools to tokenize the text. So, but actually in this case we're talking about the this one. So just for better understanding, I will just copy that one here so you have a better guide on what's really is happening. So tokenization means converting human readable text into numbers or tokens that a machine can process. So we use TechToken, the same library OpenAI uses for tokenizing GPT models like GPT-2 and GPT-3. So it's fast and memory efficient. So the tokenizer breaks text into subword units. So even the known words can be processed using pieces like, for example, we have this, or when we have like this, or also when we have this one. So this avoids the limitations of word-based tokenization, which struggles with out-of-vocabulary words. So once tokenized, each word or subword is replaced with a unique integer, and the sequence of integers becomes our input data. So now let's execute this one first, and then let's create the custom dataset. So let's title this one create a custom dataset for us to properly see what's really going on. So let's add more cells. So we're going to use this code. So this class transforms the long token stream into trainable chunks of input and target sequences. So first we encode the full text into a list of integers using encoder.encode. So for example, the cat might become a 464 or 5543. So we then use a sliding window to generate sequences. The seq underscore len defines the length of each sequence, while the step controls the overlap. So the X chunk, this one, is our input, and the Y chunk is the target. So this teaches the model to predict the next token at each position. So both chunks are converted to PyTorch tensors with data type, or with d type equals to torch.long, as you can see here, as that's the expected input for embedding layers and other neural networks components. So this class compiles with PyTorch dataset interface, making it easy to integrate with the data loaders, batch efficiently, and use in training loops. So let's execute this. Now let's go to the next step, would be creating a data loader. So we use this one. So this is actually the final step in this case. The final step is to load our dataset into batches using PyTorch data loader. Batching is critical for deep learning. Instead of training on one example at a time, so we train on multiple sequences in parallel. So we define a function that initializes the tokenizer, prepares a dataset, and returns a PyTorch data loader. So batch SZ, this one, controls how many sequences we train on at once. So more means faster training but memory usage. So shuffle through this ensures our batches are randomized each epoch. So this helps prevent overfitting and improves model generalization. The drop last true ensures that only complete batches are returned. So for instance, if the batches, or if the dataset is not, or if the dataset size is not visible with the batch size, the last incomplete batch is dropped to maintain consistent dimension. So let's execute this one. To know more about all of these things about the self-attention, please follow my videos. Until next time.